What's up, guys? Spencer here, back with another video, and today I'm going to show you how to do gradient descent, which is the backbone behind the vast majority of machine learning. So there's going to be a lot of coding, so let's get into it.
Okay, so I went ahead and got the data set loaded in using pandas to import the data set and load it in there. And then this matplotlib is just to show a little visualization before we get started. So the data set, I worked with this data set back in like September, October of last year. It's Seattle housing data. So we got 21,000 houses and a whole lot of data about the houses. And we're only going to look at the square footage and the price of houses and seeing if we can basically predict how much a house costs given how large it is. So it's really, what we're doing here is really simple. So I'll go ahead and create our X and our Y. So our X independent variable is the area. Square feet living, which is like the living space, like how much of the house is livable, basically square footage. And then Y is the price. And this Colab's editor is really handy. Pretty much can almost predict what I'm gonna write. So there we go. And if I show you what it looks like, it's known as a series, which is like a list, but like each number has a index as to where it is in the list. Like 21 number, house number 21,592. You know, it goes from zero to starts at 0 and goes up to however many houses there are. But yeah, basically that's all it is. So I'm going to show you like a little scatter plot here. What? Ah, that's right. There we go. So basically that's what it looks like. So the vast majority of these houses are under $3 million and 6,000 square feet, which given that Seattle is a pretty expensive area, I guess it makes sense that there's houses up to that mark. So let's say if we were to make a slope like y equals mx plus b, let's say like m is like, let's say that the slope is 500 and the intercept is 50,000. This is just a totally random guess, right? So this is essentially saying that the price of the house is square feet times 500 plus 50,000. So if we have a 1,000 square foot house, that would be 500,000 plus 50,000 is 550,000. Which, given that Seattle is pretty expensive, that might actually not be too far off of a guess. But the problem is we really have no idea because of just some number that I came up with in my head randomly. So the first thing that goes into this process is calculating error, which is how far off are these estimations. So we'll take in these functions, but I'm going to restart my runtime because it just needs to be done. Okay. Now, so we're going to have this function called error, and error will take in an x, a y, an m, or how about a b and an m? I like that order better. So we're gonna, for for each of these numbers, we're gonna calculate the error. So like for each house, we're gonna basically what's gonna happen is we're gonna take we're gonna predict the price given the square footage, look at the actual price, and then take in those differences as the error, and then calculate like overall how much error do we have. And we need to define n. So n is just how many data points we have. It's the number of data points. And we're going to calculate, that is, I don't know why I ran that, I didn't mean to. We're going to calculate the y hat, which is like given square footage, what our predicted price is. So we'll take y hat is equal to, and this is where we plug in more or less the y equals mx plus b function. So m times x of I, and because because if we did it m times x, we multiply it by all 21,000 values. We don't want to do that. We only want to multiply that one value. And then we're going to add the beta coefficient at the end, or y-intercept, as it's also called. And now we're going to calculate the error. So we'll start error off at 0, but we'll incrementally increase it throughout the process of this. So error and in Python, incremental change is defined as the plus equals or minus equals. And we're going to take y hat minus the actual y value, which would be y of I. So there you go. Now, there's a major problem in that problem is that essentially, what if we overpredict a house by $100,000 and then the next house we underpredict by $100,000? That would be like 100,000 plus negative 100,000 would cancel out to 0, and that would be misleading. You would think that calculate the error as 0, when in reality the error should be 200,000. So some people like to square the error to work around this problem, because a negative number squared is still positive. I'm just going to use the absolute function, abs. And in math, this would be denoted as putting, like, if you ever see like I don't know, like if you ever see like that in a math problem, that's those double lines is absolute. Anyway, so there we go. So now I'm going to show you what this looks like. And it's going to look kind of weird. What? Oh, duh. It's for I in range, not I range. Gotcha. Okay. So this is like 12 billion and something, which is like a ridiculously large number, which is kind of discouraging, because it's like, really, are my estimations that bad? My error is 12 billion. Not to mention, it doesn't really tell us a whole lot. It does, like, what is that just big number? It doesn't even mean anything, really. So what we're going to do is we're going to divide by n. So like, this is like the total error, right? But if we divide it by the number of houses that we have, we'll see what the average error is, like on average, like how far off are we in our estimations. So if I do this again, we get 561,000, which is still really bad. I mean, if we're estimating like for like luxury homes over the $10 million mark, that might not be so bad. But I mean, if we're like trying to predict average house prices and we're off by that much, I mean, that's really bad. So we're gonna have to do something about that. And this is where gradient descent comes in, because with gradient descent, we can find the best values for this. So this next function I'm gonna write is called step. I'm gonna call it step, and it'll find not necessarily the optimal value, but it'll find a better value for B and M, or it'll predict rather, but it'll probably be like massively off. So, but it'll be right in the sense that it'll know what direction to change it. Like if M is like really high, we know that M needs to be increased. If the predicted ideal optimal value for B is really high or low, or for either of these, right? If it's really high or really low, we know that we need to either increase it or decrease it. But it'll probably be like a really weird number. But what we're going to do is we're going to take a tiny fraction of it, of that change between, or we're going to take a tiny fraction of that change, and then we'll change those values in that by that much. So that's sounds kind of complicated. It's really not that complicated. I'm going to show you how it's done here. So we're going to take in all four of these same arguments, but we're also going to take in alpha, which is our learning rate, which is that tiny fraction that I was talking about, or tiny fraction or tiny percentage, however you want to look at it. Okay. So we're going to initialize these values. Yeah, these derivatives, and the derivative is these like really weird numbers that the computer thinks are better variables, basically. And we're going to start them off at our B and our M. Equals N. And again, we're going to incrementally change these. So, and we need an N again. We need an N. So now, create a for loop. And I'm offering Python tutoring in case you this type of stuff here is difficult to follow. So you may want to look into that, or free code camp, whatever, depending on your learning style or what you want to do. But anyway, so we're gonna change this. So our new B, our derivative for B, which is like this number I've been talking about, we're going to incrementally change it. So like I said, we'll start at 50,000, but it's going to change. And as I recall, I think it's going to be it's going to be lower. But anyway, we're going to take in, we're going to divide -2 by n. And this is kind of weird, but this is just, it's like a universal law, and it's a bit odd to remember, but it's just kind of there. So now we're going to multiply this number. Yeah, we're going to multiply this number by the error. So we're going to multiply this number by the error, like I just said. So we're going to take y of I, and we're going to subtract the m times x, sorry, not x of I, That's the B. And we're going to put this in parentheses so that it's it'll run better essentially. And then we're going to put these in its own parentheses. This way the values will remain separate so they don't get all lumped in together. And now the derivative for M is going to be almost the same thing. Very similar. Now, a couple differences though. The only difference is we're going to multiply the error by x of I, by the x value. And the reason for this is because generally we rely more on slope than, or one reason for this is because we rely more on slope than y-intercept when getting the right answer. So we're willing to change it more and it'll be multiplied by a much higher number. Anyway, that's some of the reasoning behind this. And now, now we're going to update these. So we're going to create a new B, and the new B value is the B, and we're going to change it by this new value of B. But we only want a small fraction of that number, not the whole thing, because then we're going to get some really crazy results. So we're just going to multiply by alpha. And now we need the same thing for M. And basically, yeah. And now we're going to return the new B and the new M value. And there we go. And if you run this, why do I keep doing this? Yeah, for I in range. So it's not for I range and it's not for in range, it's for I in range. There. And now I'm going to show you, this is just one step in the process. This should return values that are slightly different from what we started with. Let's say alpha is like 0.0001, let's say. Like I said, it's a tiny number, yeah. Okay, that. Something's wrong with the M. Yeah, the B did it right. But the M, something's wrong. Oh, you know what it was? This is a perfect learning example. So learning rate needs to be set really, really low. Like when I was talking about a percentage or a tiny fraction, I meant a tiny fraction. Still too high. So a lot of times people will do what I was about to, will fall into the rabbit hole that I almost fell into. And they're gonna think about what's wrong with their if they're doing the algorithm wrong. And the algorithm's really not that complicated. So almost all the times they're doing it right. It's just they're setting it way too high. So there we go. That's an appropriate learning rate right there. That is, in the future, I'm gonna set this to the scientific notation. But so anyway, that is how you do the step. So the next thing is next thing I'll show you is how to do gradient descent, which is basically just writing a function that performs this over and over again. Okay, so now it is time to create the function that'll actually put all this together and make gradient descent happen. So we'll just call it gradient descent because that just totally makes sense for what to call it. And gradient descent, it will take in all of the same arguments that step took, but it also takes in steps, which, as you could probably guess, is the number of times that the step function will be performed. So let's, just to make sure that it works, let's do 10, which is a very low number of steps, by the way. And we're going to take our B and our M values, and we're going to initialize them at what we had them. So 50,000 for B, 500 for M. So B equals B, M equals M, but there will be incremental change. So we're going to make another for loop. For I in range, and we're gonna iterate through the number of steps. So for each step in the 10 steps that we're performing, we're going to be changing our values of B and our values of M. So we're just gonna basically perform the step function. Pretty simple. And now that I've had alpha set to 1 to the exponent of -9 in scientific notation, it's just going to be alpha. So basically, you're just following along your x, y, b, m, and alpha. Okay, so that is how, or that is what's being taken in. Now, this is great, but the problem is, okay, so we got the B value, we've got the M value, and we know how to change it in the direction that will make the error less or lower. So we know how to change it, but we have no idea how well it's going to do. For example, like we calculated error up here, right? 561,000. And then we know that by decreasing B and decreasing M, error will get lower, but we don't know how much lower. And also, if you keep decreasing the values by enough, there'll be a point where the error starts to go back up again. So to make sure that doesn't happen, we got to keep track of the error. We got to keep track of the error. So we're going to have error. And error, we're going to basically run our error function that we made, the first function we made. And it'll take an x, y, b, and m. So there you go. Now there's another issue, and this is more personal preference, more so than like an actual like problem. But I want to have a convenient way to store this, because I want to store the results, right? Because at this point the computer is just calculating stuff, but it's not really doing anything with it. So we're going to create a dictionary to store our results. So we're going to call this just results. Nice and simple. And we start with the curly brackets, and we're going to have 3 keys in this dictionary. So the keys are going to be beta, let's call it beta, which is going to be the B value. And for starting off, the values to these keys are just going to be empty lists. And then we're going to have slope for the M value, and it'll be an empty list. And then we're going to have error for the error, to calculate the error or to track the error. So now we're going to do this thing where basically we're going to append to these empty lists here. So the way you do that is you take results. If I spelled it right, and you're going to take the beta, and you're going to append using the .append method, which is built into Python, and we're going to append the b. So basically, we're going to calculate the b for each step. We're going to calculate the new b value, and then we're going to add it to the list of betas. And we're going to do practically the same thing for the slope. And we're going to call it, the difference is it's slope, and we're appending the m value to it. And then we're going to actually, even though I set this variable, assign this variable error equals error, I'm actually not going to do that. I'm going to change that. So we're going to take results of error like that, and then we're going to append it to. We're going to append this value to it, the error to it. So now we're going to return the results. And if we run this, okay, that was silly. Steps, right? It's steps, because when you're making a function, even if you know what you're going to pass in the function, like you know that what alpha is, you know the steps and whatnot, you still need to pass. You just need to like have like kind of like a term for it, so that way it can work over and over again. So that was a mistake. So steps, there you go. So now, so like this should just be a lesson. Like, don't feel bad if you're making errors. Like we all make errors. We still all make bugs. Even, people far more advanced than me still make errors when they're coding. So, but anyway, so I'm gonna show you kind of what this looks like, and let's go ahead and assign this. I'm lazy here, so I'm just gonna make it R equals. Real setting, you would, actually, I think that would be a better example if I just do results, because if I just say R, I mean, that's very, very vague. Not the best practices, obviously. So we're going to perform this function, and we're going to have X, Y, B, M, and alpha, which is it's already set up here, so we'll have alpha, and then we're going to have steps, which for now we'll just set to 10, even though that's a very low number, just to kind of show you what happens. So now I'm going to show you the results. Yeah, so this will be a little weird looking. So as you can see, we've got this kind of sloppy looking, not sloppy, but it's just like a lot of numbers. Doesn't really look the best. But what we're going to do is we're going to make a data frame out of it. So this way it'll look a lot more readable. Okay. So basically, we've got, as we can see, the error continually decreases so far. So I'm gonna, so right now it's pretty easy to see where the lowest error is. It's because error just keeps going down. It's going to be at the bottom. But when you have when you do a ton of steps, you get to a point where, like, okay, as you change the values, the error does decrease. But then you keep changing the values further, and eventually that error starts going back up again. So you want to get to the bottom of that curve. So basically, let me show you really quick an image. Gradient descent. I don't like the, okay, there we go. So basically we're at the point where like we're starting up here and we're getting down here. So we still, and then if we did like, because we were just doing 10 steps, but if we did like 1,000 steps, we'd probably go down and then go back up. And we're trying to get to the point where we're right here. This is where we want to be on this curve. So getting back to it, let's do 1,000 steps and see how that goes. 1,000 steps. Okay, so now we've finally finished with the 1,000 steps, and the error actually, surprisingly enough, has continued to decrease. So I'm not going to make you guys wait for any more steps to take place, but the idea is you could imagine that at a certain point, there would be a point where these values would get too low and then the error would start to increase again. So just before I go, I'm going to show you just a little pandas trick for those of you who don't know, and that would be how to get the lowest error out of here, because you know, it seems like it may be kind of complicated, but it's the way you find like which I'm looking for how to locate the row that has the lowest error so that we can find the best beta and the best slope for the given formula, for the given data set. So we're going to use what's called a property, which is basically the same thing as a function. There's probably some more differences that I don't know about, but essentially the difference between a property and a function is that the function, you use parentheses, a property, you use brackets. If someone has like a more detailed explanation as to the difference, then please leave it in the comments below. But otherwise, that's the difference. So I'm sorry, it's not df, it's results. Results of error. So basically where this column is equal to the lowest value in this column. So we're basically results of error is equal to the minimum of results of error. So, okay, okay, error, there we go. And now if we look, it's at the very end with a beta of 49,999 and slope of 243. So I guess we were overpricing the houses because it's apparently the better value would be that the house costs $243 a square, or house price equals 243 time, or square footage times 243 plus 49,999. Let me just write that out. 243 times square foot plus 49,999. So there you go. And of course, these values could still get better, but that's been the video. Thank you so much for watching, and stay tuned for the next one. I've got a lot more content coming soon, and peace out.